Hello, everyone, and welcome to today's Lunch and Learn session on fast efficiency mapping for control and calibration. Your microphones will stay muted throughout the session. If you have questions, we will address them at the completion of the presentation using the Q&A feature of WebEx. However, you are welcome to type in questions at any time. Please send the questions to both the host and the presenter so we can respond. We are recording this session and the presentation will be shared. Our presenter today is Mitch Marks. Mitch has a Master's of Science in Electrical Engineering from the University of Wisconsin-Madison. He has been at HBM since 2017, where he is the application specialist for electric motor testing. He first worked as a researcher at the university, working with traction motor testing and power grid research. Mitch, it's all yours.
Thank you for the wonderful introduction, Krista. So yeah, today we're here to talk about fast efficiency mapping, specifically for control and calibration purposes, where we might have a very large number of efficiency maps. But it really applies to anybody who needs to run efficiency maps that have a high density or that might have difficult power points to hit. So we'll jump into it. So I think we have to start out with just a quick reminder of kind of the efficiency mapping process. So, we start with a test we need to run, and we have to ask ourselves, all right, I'm making an efficiency map. Is this map finished? If it's not, we move to the next torque and speed point. From there, with our dynamometer test stand, we need to set a torque and speed. We fix this torque and speed. We need to ask ourselves, are the conditions stable? Am I holding torque and speed? And we'll see an example of this a little later. If we're not, we need to wait, tick-tock, tick-tock, for that dyno to settle. If we are at a stable condition, we need to ask ourselves, are we in the temperature range that we want to test for? So again, we're waiting for that temperature to settle because machines are heating up while they're settling. Machines need to be cooled down. Next step, if we're not in the temperature range, we need to cool down. If we are in the temperature range, we take a measurement. From there, we have to ask ourselves, is this measurement good? So we actually have quite the process of stable torque and speed, stable temperature. Is the measurement good? And we have to do this for as many points as we have in an efficiency map, which sometimes is 100, 200, or more. But we're not just running one map typically, especially for control and calibration purposes. We have a whole list of conditions that we need to test for. Different temperatures, different flux states, different gears, different battery voltages. So we have to ask ourselves, once I've finished one map, have I finished all the maps? And if not, I need to move to the next test condition and run a new map. So we have all these points we need to take. Now we have all these maps. Oop, going the wrong direction. And at the end of the day, we're validating an engineering decision. So we have to go through all our engineering decisions for all of our different maps, for all of our different set points. And this can end up adding up pretty significantly. And we always have to remember that these tests can stop at any point. Somebody opens the test cell, everything shuts down. So, okay, we kind of have this complex thing where we're going from point to point creating this efficiency map. And we have to do a lot of points. Well, how many points are we talking? And again, I'm kind of setting up the problem statement. Well, let's say an efficiency map we're running, our little matrix of torques and speeds where we want to measure all the different torques for a given speed. And we want to go through set torque, set speed, take measurement. So let's say we have 10 temperatures and we have 5 saturations or fluxes that we're looking at. We want to test 5 states of charge, kind of our battery voltage. Well, okay, if each map is 200 points, we need 200 times 10 temperatures times 5 saturations times 5 states of charge. We're at a 50,000 point map. How long does a 50,000 point map take to run? Well, if each measurement point is 10 seconds, that's 139 hours. That's the better part of a week. If we have a 1 second measurement, we're at 13.9 hours. And if we have a 0.1 second measurement, and this is including just measurement speed, not those transitions, not heating up, cooling down, not user errors, 1.39 hours. So there's a pretty drastic difference. Now, with traditional equipment, a lot of people are running 10-second measurements. So they'll reduce the number of points. And I just kind of have my chart here. If you only do 20K points, all right, 55 hours, 5.6 hours, 0.56 hours. 5K points, now you're in kind of this reasonable range, this 1 week range, but you still have heating up, you still have cooling down, you still have other tests to run, you have those transitions of the dyno. Plus, sometimes Johnny the intern wires something backwards and you have to rerun a test. Or you set up, a torque offset back incorrectly, so you have to rerun a test. So the point I'm trying to make here is that these things can take a lot of time. So how can HBK help you speed this up? Because we really want to be in this range. If we can get you from 10 seconds to 1 second per measurement, we're saving a ton of time. I mean, an absolute ridiculous amount of time. All right, so what does the HBM eDrive do well? So eDrive is the product we make. It is a power analyzer. It is very accurate and very fast at measuring power efficiency. I'll touch on this in a moment. We're really good at covering complex systems. So if you have several torque transducers, you have many phases of power measurement, many motors, we're really good at mapping these types of systems as well. We can do the simple 3-phase, but also the high channel count. We do a lot of live plotting. We'll plot efficiency maps in the real time, which really give you that validation, make sure that Johnny the intern didn't wire something backwards. Get that really background and that live feedback, that intuition. Our testing is auditable, which means we store all the data. So we record every data point that goes into your power, your efficiency equations. But we also give you the equations. We show you exactly how we calculate everything. Which again, if you have to rerun a test and you missed a torque offset, you can just go back in that data, put that offset in, and effectively rerun your test through data. Really powerful. Time not on the test stand is valuable. And then we can offer feedback to control systems so that you can offer some automation tools. Really, once measurement is taken, move to next point, and cut down on some of the transition time. All right, now I get to put my money where my mouth is. How are we able to do these things? So we calculate power using a technique called cycle detect. Now, I don't have time here today to go through the derivation of power, but basically to get an accurate power measurement, you need to be at least a half cycle of the fundamental frequency and many times increments thereof. But you need to have this time between the zero crossings. We use a digital algorithm which resides in our hardware on a digital signal processor. We're in real time, in hardware. There's my pun. In real time, in hardware, we're tracking this phase A current, which I have featured in red. We're identifying zero crossings. We take 2 successive zero crossings. We call that our cycle time. And then each one of these little square waves, we give you an 18-bit power measurement. So we calculate RMS, power, efficiency, each one of these half cycles. This allows us to test very quickly. As soon as your machine is settled at a torque and speed, we can take a measurement. And we don't just give you a half cycle. We can average over a number of cycles, and I'll show that in my next slide. But even if your dyno is moving in speed, you can get a very accurate measurement. If you're trying to measure a dynamic situation where maybe you put a ramp in and you just want to take efficiency as a ramp, you can get a very high quality measurement. There's a lot of possibility enabled with cycle detect. But this is how we really get from that 10 second to that 1 second, or that 0.1 second. This is what allows us to test very quickly. And we have things like a leading accuracy, we have auto range, we can take that offline if you're interested. But the cycle detect allows us to test quickly. Accuracy we already have. So accurate measurements on the half cycle basis. As I mentioned previously, you might not want to just measure a half cycle. That's possibly a quarter rotation of the machine or less. So what I have here is my phase A current in red again. That's cycle detect looking at the half cycle in black, that little square wave. And then I have some really boring signals. I apologize for this, but this is important. If you look between my little lines here, we averaged 8 cycles together. So for this machine, I believe it was 2 full rotations of the machine. And we average our torque In pink, we average our speed. In green, we average our electrical power, so our three-phase power in lime green, our mechanical power in black, and we get our efficiency in black. Every 8 cycles, you're getting 16 half cycles averaged together. This allows for really, really accurate measurement, even at high frequencies. And again, 2 rotations of the machine is extremely fast. You know, if we look at my time scale here, that's 200 milliseconds, maybe 250 milliseconds. Very fast measurement period to get a very high quality measurement. These are a really stiff signal. You have the time alignment of the electrical and mechanical signals. Because we have this time period and we're bringing in torque, speed, DC, AC, we can average everything on the same time period. You know all the filter constants are the same. You have no distortion. You have that really high quality data. Again, extremely quickly. And all of this comes with auto range to minimize measurement uncertainty. But you can get a very high quality measurement very quickly. And you can do as many or as few rotations of the machine as you like. All right, let's see a little proof of this. So I'm claiming that we can take a measurement as soon as the dyno is settled. And here is my proof. So this is an example of a test run at a customer where we have voltage and current in blue and torque and speed in pink and green. And we can see we're holding a constant torque, or the dyno is holding as constant of a torque as it can in pink. So I have my torque as M, and we're ramping down in speed. So we're just setting a speed, taking a measurement, moving to the next speed. And we can see here that I get my RMS voltage and current, and we can see the step function. And if we look at our time frame, we have 5 seconds per division. So if I look at kind of 5 seconds per division, we have about a measurement per second. Set measurement, we get several cycles, move to next speed. This is pretty cool. Because if we look at our torque, all right, our torque flares up a little bit in the transition period. We expect that from a dyno. We're settled. And then boom, we have a power measurement. Boom, we have an efficiency measurement. Move to the next point. You can test as fast as your dyno can transition. You get this little spike, you settle, you trigger, you take a second of measurement, you move to the next point, move to the next point. That 1 second, we're now looking at a very fast test time. This also has the benefit of less time with the machine heating up and less time having to cool it down. As I mentioned previously, these tests are run for very specific temperatures. If you want to test in a 3°C window, well, if each point is 10 seconds, that's 10 seconds of measurement and likely a minute of cooling down. Now you can move through 10 set points before you need to cool down. That's really speeding up your test. And naturally, we can take all these points, so boom, trigger, 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 and we can plot those live on an efficiency map for that feedback. So it's really exciting stuff, and I'd be happy to go through this with anybody who's interested in digging into the details, but this is really cool stuff for testing quickly. And you can see your inverter efficiency, motor efficiency, and total efficiency as a scope trace. Really powerful stuff. All right, recorded data. Every data point that goes into those power calculations, we are storing at up to 2 megasamples per second for voltage and current. And I just have some waveforms from our software here. But you not only get a power value, you get all of the data that goes into it. And you also get the equations that go into it, broken out line by line. What is my time period? So what is my cycle source? What is the equation being used? And this allows you to sanity check yourself. Okay, something went wrong. Is it the data? Is it the equation? I have a model. I want to match for the equations in my model to the equations in my test, because I want these things to correlate. Or Johnny the intern doesn't enter the torque offset, and I just want to rerun the test and data. And I can go in, take my equation, pop in an offset, and then be off to the races. So there's a lot of power in this. You can save yourself time on the dyno, you can save yourself troubleshooting time, and accelerate that testing process. I've got a customer recently, I was there, and his guys had some issue. And the first thing he asked him is, can you send me a data file? Because him as the guy who runs the test stands says, you know what? I can't help you until you send me a data file. And if you send me a data file, I can help troubleshoot from my desk, accelerate that process. Lastly, we have feedback to an automation system. And this is really those transition periods. As soon as that dyno is settled, we're giving you feedback on CAN, EtherCAT, or API to your automation system so that you know exactly where the device under test is at. That dyno settles, it says, okay, we can measure, and you can trigger the eDrive system through LabVIEW, you can trigger it through C code, Python, TTL signals, so that you can automate that test and test extremely quickly. Boom, point, measure, boom, point, measure, boom, point, measure. Less time heating up, less time cooling down, more time testing other things. So with that, I know I went quickly, but I want to be respectful of your time. I'm happy to take any questions offline or in this forum right here. So thank you for your time, and I hope this is helpful.
Thanks, Mitch. Everyone, I will share Mitch's presentation with everyone who's here today. If you have some questions, we do have a few minutes here, and you're welcome to type them into the chat, and we'll respond to a few of those. Mitch, can you comment on how this type of accelerated mapping would be done for a 9-phase motor?
Yeah, good question. So because we can expand out, and I didn't spend a lot of time on this, but we can take many different powertrain configurations. So we can measure, a 9-phase machine very easily. We just add 2 cards and we bring in 3, 6, 9 power measurements. From there, we have a nice software GUI. We call it the Power Wizard, where you can configure that. And then you just get those efficiency measurements like you would for the 3-phase machine. So it's all contained in one chassis, and it allows us to test very quickly and make the process simplified.
Great. Someone's wondering if you have any comments on if they could design, by designing the test of the experiment using test reduction methods like Taguchi, that might be applied to efficiency mapping to even further reduce the test time.
Oh, absolutely. Yeah, and then that falls a little more into the test design process. But I know people will use things like, I think it's like a Monte Carlo related kind of randomization process to reduce the heating of the machine. And if you're really clever with kind of the data, you could absolutely implement that into a control algorithm. And then boom, you get a point, and then your algorithm is choosing the next one. Everybody really keeps that their secret sauce. Some people do it as simple as doing a very slow speed ramp. Some people will do heat methods, but absolutely, you could implement some sort of pattern to minimize the test time.
All right. Is it possible for the cycle detect to miss cycles?
Yeah, this is the one where all my product managers get mad at me when I say this, but yeah, we can absolutely miss cycles, but everybody else does as well. So everybody in the power analyzer business is going to miss cycles or double cycles. The cool thing about what we do is we give you that cycle detector as a trace, and you can very easily determine if you double a cycle or missed a cycle. So it's a really powerful tool. You have the data, you have the time period, you have the equations. So you can very easily see in the data where things went wrong, and then through the data take actions to correct that. So you don't need to rerun that test. And you do know when things went wrong, which you don't know what you don't know. And if you don't know things went wrong, that's bad. So we at least tell you.
All right. Well, thanks, Mitch, for an interesting presentation. And everyone, we hope you enjoy the rest of your day.
All right. Appreciate it, guys. Thank you.